When the night skies over the northern hemisphere flickered with a faint, unnatural shimmer, few realized they were witnessing the death of a traveler older than Earth itself. The object known as 3I/Atlas, only the third confirmed interstellar visitor ever detected by humanity, had just torn itself apart. Telescopes from Chile to Hawaii recorded the event: a radiant flash, a spreading plume of dust, then silence. Moments later, the data streams began to tell a story that left even veteran astronomers motionless. Fragments from the explosion were not dispersing outward into deep space, they were drifting toward the inner solar system, toward us. 3I/Atlas had entered the solar system quietly months earlier, gliding in on a hyperbolic trajectory that proved it was not born here. Its speed, over 90,000 kilometers per hour relative to the Sun, exceeded anything a bound comet could sustain. That it was an interstellar messenger, a shard from another star's nursery, crossing our domain for a fleeting moment before vanishing forever. When first observed, it seemed unremarkable, a dim, icy body perhaps half a kilometer wide, shedding a modest coma of gas, but spectroscopy revealed a signature unlike any known comet: its ratios of carbon monoxide to water, its peculiar silicate mix, and the isotopic fingerprints embedded in its spectrum hinted at chemistry forged under alien suns. For planetary scientists, it was a once-in-a-civilization opportunity, a sample of another star's debris, delivered to our doorstep. As the object rounded perihelion, the point nearest to the Sun, the internal stresses mounted. Volatile ices, long trapped beneath the crust, began to vaporize violently. Pressure built within cavities carved by billions of years of cosmic radiation. Then, on a trajectory that carried it roughly between the orbits of Mars and Earth, those forces found release. The explosion was instantaneous, a surge of light so brief it barely registered on early warning networks. In the aftermath, high-resolution telescopes captured a fan-shaped halo expanding rapidly from a bright central knot. 3I/Atlas had disintegrated. No controlled outgassing, no gradual fragmentation, this was total structural collapse. The blast velocity of the fragments reached tens of meters per second, enough to scatter material across millions of kilometers. When orbital models were run, a new truth emerged: several clusters of debris were now on trajectories intersecting Earth's orbital path. Within hours, observatories at Mauna Kea, Cerro Pareno, and the Jet Propulsion Laboratory synchronized data. The preliminary conclusion was cautious but unmistakable. Multiple fragments from the 3I/Atlas breakup display Earth-crossing components. In plain language, some of the debris was inbound. That statement echoed through every space science channel on the planet. Meteor tracking networks recalibrated their systems, amateur astronomers combed the heavens for faint, fast-moving specks. NASA convened a joint analysis group with the European Space Agency, the Japan Aerospace Exploration Agency, and independent observatories. The goal: determine size, composition, and potential impact risk. Modeling suggests the largest fragments are no more than tens of meters across, smaller than the Tunguska-scale impactors but still capable of producing spectacular atmospheric entries. Most, scientists believe, will burn up harmlessly, but their composition may be priceless. Each particle carries atomic arrangements forged under conditions alien to our solar system, metals condensed from different isotopic baselines, organics synthesized in exotic radiation fields. For astrobiologists, even a grain of 3I/Atlas dust could rewrite theories about how complex chemistry evolves in interstellar clouds. To capture them, NASA's OSIRIS-Rx-2 mission, still in planning, may be asked to sample the inbound stream. High-altitude collection arrays and atmospheric radar systems are already preparing to record the first meteoroids when they arrive later this decade. Why did the object explode so violently? The leading hypothesis is a combination of thermal stress and structural weakness. Interstellar objects spend eons in deep cold. When heated suddenly, trapped volatiles expand faster than the porous matrix can vent them. Unlike comets native to our Sun, these visitors lack the compact, sintered crust that stabilizes local bodies. 3I/Atlas, in essence, was a time capsule of cosmic dust held together by frost and memory. Its demise was inevitable the moment sunlight touched it. Yet there is poetry in that destruction. By dying, the object released the evidence of its birth, microscopic archives scattered into space, waiting for us to find them. In the weeks following the explosion, orbital analysts ran millions of simulations. Most trajectories suggested safe passage, Earth would miss the densest fragment streams by several million kilometers, but a handful of solutions showed potential intersection zones, thin corridors where dust or pebble-sized remnants might graze the upper atmosphere. These encounters would manifest as meteor storms, not disasters. Still, they demanded attention. The Planetary Defense Coordination Office issued a formal bulletin. No immediate threat detected. Continued tracking warranted. Behind the calm wording, the subtext was clear. This was a real-world test of the systems humanity had built for asteroid defense. Could we trace, predict, and respond to something that came from another star entirely? 3I/Atlas had become an unplanned drill for civilization's planetary sentinels. The event galvanized a rare harmony across scientific communities. Data flowed freely between agencies that once guarded their findings jealously. Russian radar networks shared observations with European infrared arrays. Chinese deep space monitors contributed trajectory refinements. For the first time, the term Interstellar Hazard Protocol appeared in draft form at a United Nations Science Committee. It wasn't fear that motivated this collaboration, it was wonder. Humanity, momentarily freed from politics, was staring at the same sky, watching the ashes of a foreign world drift past the sun. Peering into alien origins. Among the debris, astronomers detected spectral hints of unusual compounds, long-chain organics and crystalline silicates that shouldn't coexist under ordinary stellar conditions. That if confirmed, these materials might represent the chemical fingerprints of a planetary system unlike any we know. Some researchers speculate that 3I/Atlas originated from a binary star region where radiation gradients and gravitational tides sculpted eccentric compositions. In studying its remnants, scientists hope to glimpse how planetary chemistry diverges across the galaxy. Every particle is a messenger, a syllable in the story of a world that perished before our sun ignited. Outside observatories, public fascination exploded. Social networks filled with images, time-lapse captures of faint streaks cutting across the sky, headlines asking if pieces of another world were really coming to Earth. Pop culture seized the idea. Artists painted cosmic blossoms of fire, poets wrote of alien ashes falling like snow. What might have been a scientific footnote became a shared human myth. Yet beneath the excitement lay a quieter mood, a realization that our planet, suspended in space, is fragile. That a visitor from another star had shattered, and part of it now traced a line toward us. The distances between out there and right here had never felt smaller. Laboratories on Earth prepared for the arrival of micrometeoroids by designing collection aerogels and magnetic traps. The Stratospheric Capture Initiative plans to fly high-altitude balloons through predicted dust corridors, hoping to intercept interstellar grains before they vaporized. That if successful, the samples could answer one of science's oldest questions: is the chemistry that leads to life common across the galaxy? Early modeling indicates that some fragments contain complex hydrocarbons resembling prebiotic molecules. Should even trace amounts be recovered, they could confirm that the seeds of life drift freely between stars, linking worlds through molecular continuity. Tracking debris this faint requires innovation. Traditional optical telescopes lose the fragments quickly, so engineers have turned to wide-field infrared arrays and adaptive radar pulses. These systems sweep the sky for the faint thermal glow of dust grains smaller than a coin, moving at tens of kilometers per second. That IT is a delicate dance, predicting motion that began light years away, then changed again in the violent heartbeat of an explosion. Each successful detection refines the models, each loss reminds us how vast and unpredictable space truly is, yet persistence is paying off. A dozen verified fragments now have catalogued orbits, and at least 2 may pass within the Moon's distance of Earth in the next few years, close enough for detailed study, but far from danger. A cosmic mirror. In quiet moments, scientists speak less about impact probabilities and more about perspective. 3I/Atlas traveled for millions of years, untouched, until a chance gravitational nudge steered it toward our sun. Its destruction, dramatic and brief, became a mirror reflecting our own transience. We, too, are composites of cosmic debris, atoms forged in supernovae, organized for a blink of geological time. The explosion reminds us that creation and destruction are not opposites but partners in the same universal cycle. When the observatories replay the footage of the breakup, the screen fills with a luminous cloud expanding against black space. That IT looks, for an instant, like a galaxy being born. In response to the event, space agencies have accelerated plans for automated interstellar object interceptors, small spacecraft designed to launch within weeks of a detection. The goal is to rendezvous with future visitors before they disintegrate. That if 3I/Atlas taught us anything, it is that these travelers do not wait for our convenience, they arrive unannounced, and sometimes they die spectacularly. By preparing now, humanity ensures that the next time a wanderer from another system enters our skies, we will meet it not as spectators but as explorers ready to shake the hand of another world. Simulations suggest that fragments of 3I/Atlas will begin intersecting Earth's orbit within the next few years. The resulting meteor activity, if visible, could rival the great showers of recorded history. Imagine standing beneath the night sky as streaks from another star's debris flare and fade above you, each spark a traveler's epitaph, each trail a reminder that our solar system is not isolated but open to the currents of the galaxy. Astronomers are already naming the projected event the Atlasids. Should the dust density prove sufficient, 2030 may host a celestial spectacle unmatched in living memory. From a fragment's point of view, this journey has lasted eons, formed in the collapse of a foreign nebula, frozen in darkness, cast into interstellar night, and finally drawn by chance into our sun's grasp. It has traveled farther than any machine humanity has ever built. Now, parts of it may end their voyage in our skies, disintegrating into brilliant lines of fire. In its death, 3I/Atlas has become a bridge between worlds. Its fragments carry the story of a lost system. Our observations will ensure that story is heard. What began as a violent explosion has transformed into an invitation, a reminder that discovery often hides within destruction. As one astronomer wrote in her field notes, "We stared at the end of something ancient, and in doing so, glimpsed our own beginning." When the first of its meteors flashes across the horizon, remember this: it is not merely rock and ice that burns above us, but a fragment of the universe itself, coming home for the first time.